Morning. Welcome to Krishna's class. In this lecture, we consider two concepts, namely convexity and orthogonality in the Hilbert spaces. So, as usual, we take H as a Hilbert space over C. So, H that means there is an inner product. The inner product induces a norm. The norm induces a metric. And with respect to that metric, H is complete. That means all Cauchy sequences in H converge to a vector in H itself. If the last property that I have said of completeness is avoided, then what you get is an inner product space. Okay. So last time we introduced what are called closed subsets as well as subspaces. Okay. So if suppose M is a subset of not necessarily a subspace of H, then M is closed. If it is closed, subset of H with respect to the metric which is equal to, in terms of the inner product, so that's a closed subset. Now, M is a closed subspace. If it is a closed set, as well as it is a subspace. Every finite dimensional subspace of a Hilbert space is closed. Now this is easy to prove because you take a basis consisting of finitely many elements and every vector can be written as a linear combination of that. Then you take sequences which are Cauchy you can easily show that it converges to a vector in uh, in the space itself, in the subspace itself. Okay. But this is not true for infinite dimensional subspaces. Subspaces. For example, consider all complex valued on interval 0, 1. On the interval 0, 1. So, of course. Now L2 F complex value on and such that integral 0 to 1 is finite. Now this is a Hilbert space. It's a Hilbert space. Now the polynomials this is quite easy. So it's in fact a subspace but it is not complete. But it is not complete. Quite easy to construct an example. E to the power 0, 1. This is an element of L2 0. This is quite easy. And you see that the polynomials approximate to e power t are the collection one to n t to the power k divided by k factor. Now the partial sums of the expansion of e power t. Okay. Now this belongs to okay. Now p and t converges to e power t. E power t that's quite easy to do. Okay, right? But ft does not belong to it's not a polynomial. Okay, therefore there are Cauchy sequences which do not converge into, or there are converging sequences which do not converge in the space. It's not close. That's a very simple answer. I mean, so whatever is there in finite dimensional cases, you cannot just take it for granted that it is true in the infinite dimension. Now I take it as I leave it as an exercise for you to prove that finite dimensional subspaces of Hilbert spaces are closed subspaces. Okay, they are closed subspaces. So prove. And that's an exercise. Quite easy. Take a finite basis, because a finite basis exists. They express the sequence in terms of that. If it converges, you can show that it has to be an element of the space itself and can be written as a linear combination of the basis that we have. Okay, so that because we have seen that for any M there is a closure. So M the closure, that is a topological closure. That's quite easy to prove because I think we have indicated the proof last time. Because take belonging to a to enclosure. Converges to X, Yn converges to Y. Now this in turn implies plus Y. Okay, so it's which implies X plus Y. Similarly, alpha X. So M closure is a subspace of okay, so that is done. Now we introduce the concept of convexity. Convexity. So definition. A subset E contained in V. Now I am not necessarily is just no, we are not assuming that V is an inner product space. We will not. But an inner product space will be satisfy the same condition. Is said to be convex. It has the following. Namely, xy belonging to x belonging to V, y belonging to V implies is contained in contained. Sorry. I put it this way. Zt I take as a vector. Then of course I take this as this one. Zt to be this. I wrote it right. For T belonging to open interval 1. What is this? This is essentially a point on the segment, or if you want, you call it line segment. Line segment joining Now we will give an example. You take in unit disk. This is convex. It's quite easy to prove this. Or if you don't confuse it the other way, take it as x1, x2. This is whereas now this means the following. To take any 2 points, the entire line segment joining them is contagion. Okay? This is the unit disk. So this is your x, this is your y. That's quite easy to prove. This contains all z. Whereas suppose you take the following. The subset such that yes and no equal to 1, but not negative. That means we are talking about this set. So you can put it this way: either x1 is greater than or equal to 0, or x2 is greater than one of them. So this set this is not convex for consider the points minus half 0 and the line joining them outside the set we have considered. As I call this yes. For example, zero minus 1 by 2 but it is not convex. Okay. So one of the results that you have is this is quite easy to do because that's a linear combination. That's the basic property of the vector space. Okay. So every subspace of V is convex. Now one more theorem is that now we'll define translators. This is called the translate of E through the vector x. It is denoted by x plus. This is the definition. Now, for example, you take R2. This need not be a subspace. Any set, you can translate some x. So you take a vector x. So you take y. This is x plus y. Now run y over the whole thing. So what you get this whole thing moved through the vector x. Translating or moving every vector of to x. Be much more clear like this. See, you take function, let us consider the line. Again in R2. Suppose you take this line. Okay. So let 0, 0. Let so this is your then the translate of L. This is your L plus x. parallel to L and passing through the point now this you can prove actually. So prove this take and not zero. What is this? This is equal to equal to 0. This is the translate. Okay, you see that this is parallel to this. This is again a line in R2 which is parallel to the given line and passing through the point y1. Okay, therefore this is y plus n. Y. Let's see. So for every subset, you can translate it to any vector. Okay, you get another set which looks in shape essentially the same. You have a geometrically conceivable scenario, then you get another set of the same shape, but translated a corresponding distance. Every vector will be translated to that vector. This is the idea. Okay. So this is the geometry is this. Suppose this is your A1 then you take any point on x equal to x1, x2, y this vector y1, y2. What do you do? Take x and translate it. How do you translate it? You complete the parallelogram. Take x plus y. So this point is that, and in fact you take every point here and translate it. This would be this is the line that this is going to be L plus Okay, that's the geometry of the problem. Now we define what is orthogonality. Definition. Suppose x comma y belonging to H. Now here we take H to be an Hilbert space, at least an inner product space, so that you can, all the statements that you make do make sense because you are going to use inner product, are said to be mutually orthogonal if x, y, 0. Inner product of x with y is 0. What does this mean? Let's look at it. So this is a vector. Now which vectors are orthogonal? In fact, you see that you draw a line orthogonal. So this is the any point on this is y. Now you see that x dot y is equal to 0. Because in R2, it's the inner products that we are taking is the dot product. Okay, so x dot y, so you get a whole line. Okay, so clearly that's why you say mutually orthogonal. Okay, that's very clear because you see that inner product of x with y is the same as inner product of y with x conjugate. Okay, this is because so if xy equal to 0, that means inner product of y with x conjugate is 0, which means inner product of y with x is 0. So y is orthogonal. That's a simple aspect. Here you see that you are given a non-zero vector x. Now you see that the set of all y which is orthogonal to this. Now if y is orthogonal to x, then you see that alpha y is also orthogonal to x. Therefore, this whole line spanned by the vector y is orthogonal to x. Okay. Therefore, we will infer one more thing, that suppose you take x defined by x where equal to 0. That is all those vectors y which are orthogonal to this is same as y now this we designate by x with a symbol like this, which is read as xper. Okay, this is called xper. X symbolically is. Okay. Now clearly one of the things that you can prove is this. Okay, let us look at the trivial situation. Equal to 0. Means every vector in and this is a property satisfied by every, this is H. So that's a trivial. If X is not equal to 0, then this is a proper subspace. So we shall define. So given the set M-pair by to set of all y belonging to H such that y is orthogonal to X for every X belonging to So what is this actually? Just work it. Then you observe that M-pair is a subspace of H. Why? Because if y1 belongs to M-pair and y2 belongs to M-pair, then y1 plus y2 belongs to M-pair. So also scalar multiple of y also belongs to M. That's the reason. It's very simple. And so that is the proof for that. But what is this? This also can be written as the 4. Intersection x pair for x belonging to H. Okay. Now this is quite easy to show that this is. Okay. So x bar is the set of all y which is orthogonal to x. And when it is orthogonal to every x in M, then you get the intersection. Now the first result is, why? Because suppose this is equivalent to saying that is norm of or now claim equal to 0. So you see that xy is essentially equal to since a continuous function. Right. Because it is continuous. A continuous function. Therefore, what do we have? It implies zero, which is equal. So experp is a closed subspace of now M pair so this is the intersection of closed subspaces of that arbitrary intersection of those sets are closed. Therefore, M pair is a subspace which is closed. Which is closed. Now we prove a very important theorem, but let me just put it off to my next lecture. It's an important result, so we will do that next time. Okay. Right. Thank you very much.